A major hurdle in the correct use of confidence intervals is in their interpretation. And the big problem that arises in trying to interpret confidence intervals is that they're actually quite challenging to interpret correctly. The reason being is that in order to form a confidence interval, we rely on a probability definition for what the confidence interval is actually going to be. So it's going to be an interval that contains the true parameter with some set level of probability. However, this is a statement about the estimator of the confidence interval, about the interval estimator itself. And the estimators are just a process for generating estimates. And so once you're actually holding some specific confidence interval, once you actually have calculated something using data, this probability interpretation is no longer relevant. And because of that, knowing what to do with a specific interval can be quite challenging. So the interpretation of a confidence interval, at least in terms of the probability interpretation, is going to be based on the process of forming the intervals, not on the estimate itself. So when we say there's a 95% chance that this interval is going to contain the true parameter value, that is based on using that procedure rather than on whatever interval we have gotten out of that procedure. Okay. So in order to define our confidence interval, we take this set probability, 1 minus alpha, and there's going to be that probability of the true parameter value being within the interval that we're interested in. Now, it's calibrated based on the estimators, which are random variables, not based on estimates. Right? And so if we think about the lower bound and the upper bound as being two different estimators, an estimator for the lower bound and an estimator for the upper bound, then those are the random components of the interval. Right? And because those are the random components of the interval, once we have specific values for that, there is no randomness left anymore. And so it's no longer correct to make probability statements, or at least to make the types of probability statements that we might want to make about confidence intervals for these specific values themselves. So before the data have been observed, we can use this probability interpretation to discuss them, right? So you can say that by using the confidence interval procedure for the mean, there's a 95% chance that my 95% confidence interval is going to contain the true mean. But once you have a specific interval, you can't use that probability-based interpretation anymore. So what do we do, right? Once we actually have an interval, how do we go about interpreting that specific confidence interval? Now, the issue that we're going to sort of be bumping into here is that once you have estimates, those are just simply numbers, right? So once you've actually calculated your confidence interval, that's just going to give you some set number about from which your sort of interval is actually derived. Okay. Also, remember that the parameter value, while we don't know what the value is, we're assuming that there is some specific value, right? There is a real population mean or a real population proportion out there. We just don't know what that value happens to be. And so we have estimates that are just numbers, and we have a parameter that's just a number. And so what we're really thinking about here is you can envision us having come up with our interval, and our interval is something like 3 to 7. Right? This is the confidence interval that we have calculated. And while we don't know it, perhaps the mean in the population is 5, right? And so then what we would really be asking by saying, well, what's the probability that the mean is in the interval is, what is the probability that 3 is less than or equal to 5, which is less than or equal to 7, right? What's the probability that 5 is in this interval? And the concern here is that if we just look at this statement, well, 3 is less than 5 and 5 is less than 7, and so this probability has to be equal to 1, right? This first probability here is exactly equal to 1 because it's true, right? This actually happens. 3 is less than 5 is less than 7, so that's equal to 1. But we could consider a different interval, right? So what if instead of the parameter being 5, we said the parameter value is 10? Right? So now, what's the probability that 3 is less than or equal to 10, which is less than or equal to 7? Well, that doesn't hold, right? So this is going to have to be 0. There is no probability that 3 is less than 10, which is less than 7. Right? That doesn't happen. It can't happen. And so the probabilities associated with these events become either a 1, as in this first case, or a 0, as in the second case. And so this is really the fundamental problem with this probability interpretation here, right? So if we are thinking about are specific realizations, right? So lowercase l less than or equal to theta, less than or equal to lowercase u. Well, these are all just numbers. And so these types of probability statements here, they're sort of no longer relevant. Our probability that the true value is in the interval is always going to be either 0 or it's going to be 1, right? So we can sort of just make that statement very deliberately here, right? So the probability of the true value in the interval is either 0 or 1, right? The probability that the true value is in the interval is either 0 or it's 1. If we know what the true value is, we can say, is it a 0 or is it a 1? If we don't know, all we can say is it's either a 0 or it's a 1. It's nothing else. It can't be 95. It can't be 99, right? It's either there or it's not there. And so because of that, right, we have to sort of turn towards other types of interpretations for these statements. Okay. So in order to sort of think about this, I want to take sort of a visual example to help sort of clarify this point. So in my hands here, I have two different markers. I have this red marker and I have this yellow marker. And what I'm going to do is I'm going to put them behind my back and I'm going to start mixing up these markers. And then I'm going to put one of them into my right hand at random. Okay. And I want you to be thinking about is right now, what is the probability that the red marker is in my right hand? Okay. And so if I actually mix these up perfectly at random, then the probability that the red marker is in my right hand is going to be 50%, right? Before you've seen anything, if we assume that this is all a fair process, then it's a 50% probability, 1 and 2, okay? But now I can show you in my right hand, I have the red marker. And so at this point, what is the probability that the red marker is in my right hand? And of course now, well, the red marker is in my right hand. And so because of that, this is a probability of 1. Right? If I were to ask you, what's the probability that I'm holding a red marker in my right hand right now? The only acceptable answer is, well, it's a probability of 1, right? And if we had come out and seen the yellow marker instead, and I ask you, well, what's the probability that my right hand is now holding the red marker? It's now a probability of 0, right? So before we've actually seen the process happen, when we're at this stage before we've made any observations, we know this procedure is going to result in a 50% chance that I'm holding the red marker. Right? But as soon as we actually take any realization, then it's either going to be a 100% or a 0% chance of actually seeing the red marker, right? And so there's this difference between the procedure that we're thinking about and the actual realizations. The same thing is happening with the confidence intervals. The confidence interval is a procedure that's going to give you a, say, 95% chance of having the true value in there. But once you have a specific interval, it either is or it isn't. There's a 100% or a 0% chance. And so just to walk through that example sort of in words, right? So what's the probability if I place the two markers behind my back and choose one at random that I draw the red one? Well, that's a 50% probability, right? But if I show you that I actually drew the red marker, now there's a 100% chance. And if I show you that I did not draw the red marker, well, now there's a 0% chance, okay? And so the interpretation of the probability statements change from when we're thinking about the process to when we're thinking about the actual observations, right? The process has a 50% chance, but the observations are either 0 or 100. So we can think about our 95% confidence interval for the population mean is going to be fit. And so what's the probability that the interval contains mu? Right? So at this stage, we have a process that we're going to follow to fit a 95% confidence interval, but we haven't actually followed it yet, right? And so when we're at this stage, we can say, well, there's a 95% chance. If we go out and we follow this procedure, there's going to be a 95% chance. That's what a 95% confidence interval actually means, right? So there's going to be a 95% chance that it's supposing it's a correctly calculated interval, that the truth is contained in the interval. Now, suppose that the interval is computed and we find that it is 1.2 to 9.2. Now, what's the probability that mu is contained in the interval? Okay. And here, we have to be careful. We can't say that there's a 95% chance anymore because now we don't have this randomness. We've already seen the marker, right? It's sort of, the estimate has been calculated. And so either there's going to be a 0 or there's going to be a 1 probability of it. We don't know which one it is, right? But we can't say it's going to be 95%. It will be either 0 or it will be 1. We don't know which of these it is, but there's no longer randomness. It's either definitely is or definitely is not happening. What if we knew that the population parameter value was 10, right? So now we've calculated this interval, it's 1.2 to 9.2. We know that the truth is 10. What's the probability that the interval contained the truth? Well, here we just take a look and we say, is 10 inside of this interval that we're calculating here, right? So is 10 inside of this interval? And no, 10 is not inside of that interval. And so because of that, it has to be 0, right? This is 0 because 10 is not contained inside the interval. What if we had gotten 6.4 as the true value, right? So the actual truth we somehow come to learn is 6.4. Well, 6.4 is inside of this interval. And so because 6.4 is inside of that interval, right, then we can say, well, there's a 100% chance, right? The probability is 1 because 6.4 actually is in the interval. Right? So we start with the 95%. Once you've calculated, it's going to be a 0 or 1. It's a 0 if the truth is outside of the interval. It's a 1 if the truth is inside of the interval. Okay. So with all of this, right, the question remains, why do we use specific intervals then? Or how can we use specific intervals then, right? So if the probability interpretation for specific intervals is not useful, then what can we do with specific intervals? How can we interpret specific intervals? And what I would say is that there's broadly, the intervals are going to give a range of plausible values, all of which are well supported by the data, okay? And so that's really what we're thinking about with these specific values. So in a sense, the data aren't going to be sort of picking between the different values within the interval. Any value in the interval is sort of an equally good representation of the truth, okay? And so just because you have, say, 1 point estimate, right, what your confidence interval is going to be saying is, well, you can take that point estimate, but you can move it up or down a little bit, and there's really no difference based on the data. There's no reason that you would pick one of these values over another one, at least to some degree of confidence. Okay? So that's sort of the idea, is that within these intervals, these are all plausible values. Any of them are sort of equally good. But there are other ways that we can sort of make statements about specific values. And the one way that you'll see come up quite often is to use the term confidence rather than probability. So we might say that we have a 95% confidence that the interval contains the truth. And what do we really mean by this? Well, what we mean is that if we're going to repeat the process many, many, many times, then in some percentage of those cases, the truth is going to be contained in the interval, right? So let's say we're fitting a 95% confidence interval. Okay. What this means is that if you were to go out and you were to fit this 95% confidence interval, and then you take another sample and you fit a 95% confidence interval using the same process, and then you do this again and again and again and again, right? And you continue doing this forever, then 95% of the time, the intervals that you calculate are going to have the truth in them. You can't say anything about any one specific interval that you do calculate. However, if you were to repeat this over and over and over again, then 95% of the time you're going to. And we can refer to this as saying there's a 95% confidence in this interval, right? And so that language of confidence, it's not a probability statement, but it is a statement that sort of refers to the procedure, right? We know if we follow this procedure over and over and over again, there's some probability. So when we follow the procedure only a single time, we're somewhat confident in the result. So if you say we're 95% confident that the truth is contained in the interval, then that's really a shorthand for saying if we were to repeat the process over and over and over again, then 95% of the time the truth is contained in the interval. In other words, most of the time, if you have a 95% or a 99% confidence interval, you're going to be right? Most of the time, the interval is actually going to contain the truth. The other thing that we can do with specific intervals is to consider the width of them, right? And so in some sense, we want a narrow confidence interval. If we could have a very, very narrow confidence interval, then we're saying that there's sort of a lot of precision about what we think the actual true value is. And that is better for us in the sense that we're more confident that it's within a narrower range, right? And so the width of the confidence interval gives us some level of measure about the uncertainty that we have in the given scenario, right? So wider intervals are going to express more uncertainty about the parameter values, whereas narrow intervals are going to express less uncertainty. And so if you take a look and you see a very wide confidence interval, then what we're really saying there is that in order to be some level of confident that the truth is in this, we need a lot of variability. So that probably means that it's a difficult estimation problem, that the data are quite variable, variable, that we don't have a lot of information at our disposal, that we're not really sure about the values, right? There should be sort of less trust placed in any specific value in that case. But if you have a very narrow confidence interval, then you can be a lot more certain that the true value is somewhere around there, right? We can sort of get a lot more precision. We can feel a lot more confident that that range sort of contains the truth, that the data are of higher quality, that we have less variability there, that it's an easier problem, right? Any of these types of conclusions here. So it tells us both what do the data look like, how much variability is there, but also what can we know from the data, right? And so using the specific interval, right, we can think about them as giving a range of plausible values. We can think about them as being calibrated to some set level of confidence. And in order to sort of understand that, we need to be thinking about repeating that process over and over and over again and knowing that we're going to be right most of the time. Or we can think about the width of the interval, right? And the width of the interval is expressing some level of uncertainty about what's going on. Okay. So overall, confidence intervals can be challenging to interpret, and they're frequently going to be misinterpreted, right? And so the hope with this is to really think about how there's the probability interpretation of the process, but that doesn't apply to the specific intervals themselves. So confidence is not probability. And so in order to interpret a confidence interval, we need to turn towards confidence. We need to turn towards thinking about the width, or we need to think about this as giving a range of different plausible values. We're not thinking about this as being a calibrated probability statement, because the probability that the true value is in any specific confidence interval is always going to be either a 0 or it's going to be a 1.